All right, let's dive right into this. Welcome to today's explainer. We're going to tackle one of the absolute most mind-bending, reality-breaking glitches in the very fabric of our universe. We're talking about the paradox of the quantum. And more specifically, we're going to unpack something called wave-particle duality. Now, I know, that sounds like some serious, intimidating science jargon, but stick with me. By the end of this, you're going to see just how deeply weird and honestly absolutely fascinating the fundamental building blocks of our reality truly are.
So, at its core, what exactly is wave-particle duality? Well, it's the proven fact that matter and light can behave as both waves and particles, and it depends entirely on the experiment you're running. Yeah, you heard that right. The actual stuff that makes up everything around you, and the very light you use to see those things, well, they're constantly playing this cosmic game of dual identities. It's kind of like a fundamental glitch in how we all assumed the universe worked.
Okay, moving into Section 1, the quantum paradox.
When you first hear this concept, it sounds, well, absolutely impossible, right? It totally defies all common sense and everyday logic. But here's the thing. Things at the quantum level can actually exist in two seemingly contradictory states at once. To really wrap your head around how crazy this is, think about an ocean wave crashing on a beach, right? Now think about a single, solid baseball. They are completely different phenomena. A wave is this spread-out disturbance, it flows and ripples, while a particle, like that baseball, is a single concentrated object with distinct, hard boundaries. I mean, you can't have a baseball that ripples through a window, and you definitely don't have an ocean wave that exists as a single hard dot. But down at the microscopic quantum level, the universe flat-out refuses to choose. A single quantum object actually has the characteristics of both. Mind-blowing, right?
That brings us to Section 2, classical versus quantum physics.
To really grasp the sheer magnitude of this discovery, we kind of need to look at how science used to view the world. In the comfortable, intuitive, old rules of classical physics, things were, neat and tidy. For literally hundreds of years, classical physics stated that light was a wave, pure and simple. And things like electrons, well, they were considered particles. Boom, case closed. But then, we discovered the messy, complex, and frankly astounding quantum reality. Quantum physics came along and showed us that both light and matter can show wave-like and particle-like behavior. Our entire foundational understanding of the physical world wasn't just tweaked a little bit, it was completely flipped upside down.
All right, Section 3, seeing both sides.
Now you might be sitting there asking, how do we actually know this? Scientists didn't just wake up one day and guess that matter behaves like waves, right? Let's look at the hard evidence. Take light, for example. We know light acts like a wave because we can literally see interference and diffraction. That means we can watch light waves bend around obstacles and overlap to create very specific patterns. But through phenomena like the photoelectric effect and Compton scattering, light acts exactly like a stream of tiny, solid bullets, physically knocking electrons out of place. It actually behaves like physical matter. Then, if you look at electrons, we know they're particles because they literally have mass and momentum. They carry physical weight. But shockingly, we also see they can produce interference patterns, exactly like ripples spreading out on a pond. Depending on how we test them, they show us a completely different face.
Which leads us to this definitive, incredibly powerful realization. Quantum objects do not fit classical categories. I really want you to take a second and let that sink in. It's not that our microscopes aren't powerful enough or that our instruments are somehow flawed. It's that the fundamental building blocks of reality simply refuse to fit into our neat, human-made traditional boxes. They behave like waves in some specific situations and exactly like solid particles in others. So, the natural question here is, what actually happens when we test this directly? If an electron is both a wave and a particle, what does it actually look like when we force it to show its hand in a laboratory? How did scientists practically prove this invisible quantum weirdness to be true? Well, let's look at Section 4, the double-slit experiment.
This brings us right to the absolute climax of today's explainer. If you only remember one thing from this whole analysis, please make it this. It is arguably the most famous, reality-breaking experiment in all of modern science. I'm going to guide you through these steps carefully because this is where the nature of reality gets frankly completely unhinged. Step 1. Scientists fire a stream of particles, let's just say single electrons, toward a solid barrier that has two tiny parallel slits cut into it. Step 2. You'd expect them to just fly through the slits and make two solid lines on the wall behind it, right? Kind of like bullets. But instead, they create an interference pattern. It's this complex series of multiple bands that you only ever get when waves ripple and overlap with each other. Okay, so a single solid electron acts like a spread-out wave. But here is the mind-blowing twist in step 3. Scientists wanted to see exactly which slit the electron was going through, so they set up a microscopic detector right at the slits. The moment they turned that detector on to individually measure the electrons suddenly stopped making a wave pattern. Yep, they acted like normal solid particles again, hitting the wall to make just 2 neat, predictable little lines. You turn the detector off, you get a wave pattern. You turn it on, you get a particle pattern. Which brings us to step 4, the most shocking scientific realization of our time. Observation affects outcomes. Just the act of looking, the mere act of measuring the particle, literally changes the physical state of reality. I mean, no way, right?
Which brings us to our final part, Section 5, Why It All Matters.
I know. That sounds like magic or maybe deep philosophy, but it's hard, proven science. So why isn't this just useless trivia for a bunch of physicists in laboratories? Well, because this strange reality is literally the foundation of the modern world. First off, this discovery completely changed our understanding of nature. It proved that classical physics was incomplete and led to the creation of an entirely new field, quantum mechanics. And practically speaking, this strange wave-particle duality made modern electronics possible. I mean, the smartphone in your pocket, the microchips in your car, the very screen you're using to watch this explainer right now, absolutely none of them would exist if engineers hadn't learned to manipulate electrons using the bizarre laws of quantum physics. And looking to the future, it has paved the way for quantum computing. That's a technology so powerful it promises to revolutionize medicine, artificial intelligence, and even global security.
And this brilliantly brings us to our ultimate one-line summary. Light and matter can behave as both waves and particles depending entirely on how they are observed. Just think about the gravity of that for a second. The very fabric of light and matter shifts its identity based on observation. It leaves us with a truly provocative question. Does simply looking at reality literally change it? Well, the quantum universe seems to say yes. Thank you so much for joining me on this explainer today. Keep exploring, keep questioning, and I really hope this leaves you looking at the world around you just a little bit differently.